Okay, guys, there seemed to be a lot of confusion on what's the point of this lab. You're trying to make sense of it. So I'm going to try to clarify some of this stuff, what the two graphs mean. So first of all, in the introduction, the background information from the lab, if you read right here, it talks about Beer's law. Spectrophotometer, when you use spectrophotometry, you can create a calibration curve, and that will relate the raw absorption, like how much of that substance will actually absorb the light, and then kind of relate that to its concentration. So things that have color will absorb light. Things that are transparent, like the sodium hydroxide and water, the light passes right through. So the crystal violet is the one we're focusing on because that's the one that has color. And we're seeing how the absorbance changes when the concentration changes, because when the concentration changes, the color actually changes. So you did a calibration curve with multiple dilutions of crystal violet, and it gave you different intensity of violet colors. And so you were able to read the absorbance off those different concentrations. So Beer's law relates concentration to absorbency based on this formula. Now, A and B refer to the molar absorptivity and the path length, meaning the cuvette, how big the cuvette is. Well, all of this stays constant right here. So all we're focusing on is the concentration and its absorbency. All right, so by doing this, if we figure out the calibration curve, then we can go ahead and do a reaction with the crystal violet and sodium hydroxide to predict. So down here, this enables you to predict the behavior of that system because the raw data that we get, we can put them into our graphs. So we will have concentration versus time, natural log concentration versus time, and 1 over concentration versus time. So if we can graph those out, we can figure out which one will give us the straightest line, and that will predict what order that the crystal violet is affecting the rate. So if it's 0 order, then the crystal violet has no effect on the rate. If it's first order, then it's directly related. So if you double the concentration of the crystal violet, you'll double the rate. And if it's second order, if you double the concentration, well, that'll increase it by 4 times. So that's kind of what it's saying here. So again, if we looked over on the back side, the next page over here, here's our reaction taking place. We have crystal violet reacting with the hydroxide to make this aqueous solution, which starts to clear up. So our rate law for this reaction will be the crystal violet and the hydroxide. But the hydroxide is staying constant. We're not changing its concentration. It's the crystal violet that's changing its concentration. So our new rate law is just concentrating on the crystal violet and how the rate changes, the time. So when we do our graphs, I'm going to pull these graphs up. You had your first graph that you had to kind of create, which is your calibration curve graph. So you get something like this, where you have your different concentrations of the micromolar, 5, 10, 15, 20, and I have 25. You can't see it, got kind of cut off over here. You graph it out, and you find the slope of it. So the slope is going to give you your constant. So concentration versus time kind of brings us back to that Beer's law equation. So the slope is the value we're trying to find that we can put in to our integrated rate laws to figure out what the to get the graphs for those three. So my little example here, my slope is 0.05428. So when I go and I do my 3 different graphs, one of concentration versus time, and the other the natural log of the concentration versus time and 1 over the concentration versus the time. I get a variety of different graphs here. And so the slope is used so that we can convert the absorbency into concentration. So again, if I go back, looking at Beer's law, this slope you got right here came from this law right here. Okay, so we're looking at the relationship. So kind of AB is kind of your slope that you're looking at. And when I use this slope to convert absorbency over to concentration, sorry, keep going back and forth. I'm going to go here. I just put the absorbency values in, the variety of ones that I got, and I divide by the slope, and that'll give me the concentration. So that'll help convert the absorbency into concentration. And then from there, you can make your 3 graphs. So once you have your concentration, then you just take the natural log of each of those concentrations to get for the first order, and then 1 over the concentration to give you the second order. And again, whichever graphs gives you the greatest correlation, closest to 1, would be the rate order for this reaction. So I hope this kind of clarifies some of the misunderstandings and what you're not quite understanding. If you're still having problems with it, send me a remind text, and I can try to address it from there. Anyways, good luck, guys. Have a good weekend.